Hello, welcome. My name is Kasole Bennett, and I'm a student. Registration number with my student number over here. And today I'm going to go through reinforcement learning for Wingcraft control tasks. And now my research, I've picked it from the IEEE, that's the source I've used. And the date of publication is 25th July 2024. So reinforcement learning, what maybe an insight? Reinforcement learning to me, and maybe to other scholars, they define it as a branch of machine learning where an agent learns to make decisions by interacting with the environment to maximize a reward signal over time. That's how I can define reinforcement learning. Therefore, we're saying that RL, what we call reinforcement learning, has been studied for many years already, but has just seen its biggest jump in popularity and applicability in recent years. And then we're also saying that a lot can be attributed to me, a tab, as a researcher and an academician, and actually the one behind the DeepQ or the DeepQ network methodology, which successfully implemented the DNA, or what we call the deep neural network, into traditional reinforcement learning workflow. Now, in this brief research I've conducted, I'll briefly talk about the following areas in relation to my area of research: fixed wing aircraft control tasks. So I'll talk about the computational problem that the researcher was trying to handle. Also, I'll talk about the approaches used for model evaluation. I'll also talk about the thought process of the authors, and then the data sets that were used. And finally, I'll look at the evaluation metrics and try to weigh them, looking at the strengths and the weaknesses of each evaluation metric that was used. So, coming back now with the computational problem that we tackled, we realized that this paper was focusing on RL applications. I said whenever we meet RL, I mean reinforcement learning. So it focuses on RL applications in fixing wing aircraft control, addressing challenges such as altitude control, slope navigation, landing, and multitask learning. One of the main computational problems is complexity of flight dynamics, which require continuous control, multi-degree of freedom, maneuvering would be the weather or some other interferences, and real-time decision making. So this research highlights the difficulty in standardizing reinforcement learning benchmarks in aviation due to difference in simulation environments and the evaluation criteria. What is the evaluation criteria in this case? The evaluation criteria helps us to ensure efficiency, performance, and compliance with aviation regulations, which might be the design, the testing, certification, and the operation of the aircraft. So all those ones fall under the evaluation criteria. So I also talk about the approaches used for model evaluation. Simulation-based testing, the RL models are primarily trained in high-fidelity flight simulators like JSDSim, which provide accuracy or accurate physics-based flight dynamics. That is the main purpose of the JSDSim. Now, also, if we look at another model evaluation, we talk about the task-specific performance metrics, that we look at each reinforcement learning model being evaluated based on how well it can perform the given task. For example, the head stability, the height maneuvering, the accuracy, and successful landing. Also, the reward shaping and performance comparison. So the reward function is designed to measure agent success, penalizing deviations from desired behavior like collusion and loss of control. Let's not forget that with reinforcement learning, we aim at having a reward. So where you win, a reward is given, and where you lose, of course, there is a penalty. However, the universal benchmarks makes comparisons across studies a little bit hard. So the value-based reinforcement learning, training the Q-learning, the DQ networks, so DQN and double DQ networks are explored for this discrete action control. So those are the evaluation metrics or evaluation models that were employed. So what were these maybe researchers and the writers all about? What were they thinking about? So to address gaps addressing gaps in fixed wing reinforcement learning research. So you realize that the most RL aviation research focuses on quadcopters, living fixed wing aircraft and studies. So in this case, we wanted to enlarge our study, putting aside quadcopters and maybe also focusing on fixed wing aircraft. So the authors curate and analyze 48 papers to bridge this gap. And then the other one is emphasizing standardization. Of course, the aim would always be improving on whatever things would be currently employed in place. So emphasizing standardization advocates for benchmarking datasets and standard evaluation metrics in reinforcement learning for aviation. Number 3, the other thought is that focusing on autonomous control. This one suggests shifting from manual control to AI-driven automation using multitask reinforcement learning. Let us not forget that with RL, we also focus on a lot of AI, what we call artificial intelligence. So the data set used synthetic simulated data. Now, this one is used due to safety and feasibility concerns. All models are trained in JSBSIM based on custom-built simulators. Let's not forget the purpose of JSBSIM. We said that the main purpose is to provide accurate physics and physics-based flight dynamics. So that's why this one was also employed here. The state and action spaces variables include aircraft position, velocity, angular rate, control surface positions, and the rest. So these are the data sets that were used. And then conclusively, I also want to go through very fast the strengths and weaknesses of the models and evaluation metrics. So we have the aspect here of the metrics, the strengths and its weaknesses here. So the value-based reinforcement learning models, these ones, they work very well for discrete action, well-researched, effective for simple tasks like head controlling. This is actually the main strength of using the value-based RL, the DQs, the DQNs, and the rest. But the main weakness here comes with continuous struggling to control. It needs extensive training of the data and the data sets, so it becomes a little bit tiresome and hard. So the other of simulation testing, it is safe, cost-effective, physics accurate flight models. Of course, when we see JSPM, let the physics accurate flight come to our minds. So this one, since we are saying it is simulation, we realize that transferring it to real life or sim to real transfer, it still remains a challenge. The other one is task-specific metrics. These ones, the advantages in that they directly measure flight performance, for example, the heading of the aircraft, the stability, and fuel efficiency. But however, it might also have some drawbacks that there is no universal benchmark for comparing these different models. And then the reward optimization, it is adaptive rewards which enable to improve training or to make training more efficient. So at the end of all, this one develops some weakness in that there is always poor reward shaping, which can lead to undesirable behaviors. So briefly, these were the strengths and weaknesses about the metrics or the evaluation methods or metrics that were employed. Now, conclusively, if you go on to read that paper, we realize that the paper explores different algorithms, the effectiveness in simulated environments, and then the challenges in standardizing evaluation methods. So they would suggest moving towards universal benchmarking, multi-task reinforcement learning, and increased automation in the future. So briefly, that's what I can say about the research that I've conducted. Compliments are welcome. Thank you for watching. Goodbye.